backwards adaptable. The amounts we know about what is truly being released will improve over time, especially as we start cutting emissions. The critical piece is to not wait for perfect data. We know enough to cut emissions today. Yes, we know, but we need to continue to work really to improve our knowledge. I'm also very glad that head of Florence School of Regulations gas area, Ilaria Conti, has joined us all today, and I would give the floor to her for a short welcome. Ilaria, the floor is yours.
Many thanks, Andris. Hello, everybody. Thanks for the invitation, Andris. I'm very happy to be here and open this, I think, extremely timely online debate. Extremely timely because, as you just reminded to us, methane emissions has been really in the spotlight at the COP26, which has recently concluded. So, of course, the commitment and the global methane pledge was, of course, a very big news, and is encouraging us to keep looking into the important issue of methane emissions. There is also the upcoming methane emissions mitigations legislation expected soon. So it's very important to keep the attention high on this important topic. And it's also essential to keep our efforts united. That's a typical example. We are connecting people from all over the world, even today in this online debate. And particularly, it's important to keep researching on these topics that are honestly fairly new to most of us. So thank you very much, Andris, for organizing this online event together with the Environmental Defense Fund. I'm really happy to be here with you today, and thank you very much for your excellent work. I wish you a very good debate.
Thank you very much, Ilaria. So we could move to the session one, the current state of meat and science. We would be very happy to start with a keynote presentation from Vaishali Naik, but I don't see her at this stage. I think she has not yet joined us, but I hope that she will join soon. And I would just, in the process of her joining, to introduce her. Vaishali Naik was coordinating lead author on the chapter on short-lived climate forces and contributing author on Annex 2 in the IPCC's 6th assessment report. She is a physical scientist at the Geophysical Fluid Dynamics Lab based at Princeton University. She works in division of biogeochemistry, atmospheric chemistry, and climate division. She has rather fascinating researcher story, and she studies interaction between atmospheric chemistry and climate. Basically, the impact of climate change on air pollution and how air pollution affects the climate. So I hope that she has joined us. No, I don't see yet. Vaishali is not there. Yeah, my apologies. So if it's okay with Thomas, I would like to give the floor to Thomas Röckmann. He's professor for atmospheric physics and chemistry at Utrecht University. He has spent quite a time at Utrecht since 2005. His research is on pathways to sustainability. He looks also in one of the project on Arctic methane, and his research interests are related to development and application of isotope techniques to investigate physics and chemistry of the atmosphere. So, Thomas, sorry to change the order, but please be so kind, and the floor is to you.
Yes, thanks a lot, Andris. I'm happy to jump in here now. It will be without a big introduction on the session here. I was asked to present our work in a search and research project that we did together with a couple of European research institutes. I will share the screen in a second. Just to put it in perspective, this is basically also to get an idea how to establish a baseline for emissions for one important fossil fuel production region in Europe. And with this in mind, I will share my screen now. Can you see my screen?
Yes, we do. Yeah, perfect.
Okay. Good. So I want to present you the big framework of our project ROMEO, which is the acronym for Romanian methane emissions from oil and gas. And as I'm the PI of this project, I'm also the coordinator of a Marie Sklodowska-Curie training network, MIMO Square, that we had in the last years, and where we actually put together our consortium of scientists to focus on one important fossil fuel production region in Romania. And I work at Utrecht University, as you have already said. So you may wonder why we focus on Romania. Of course, emissions need to be reduced. We need to find out where emissions can be reduced more effectively. And when we started this project, we had maybe I can get my pointer. We had informations of emission numbers reported to the UNFCCC on emissions from oil and gas production, distribution and use that you see here on the right-hand side. And you see that Romania is really had at that time, in 2013, the highest reported emissions. Why is that? Because there's a high production of fossil fuels, and when there's high production, there will also be some leakage, so there will be some emissions. And of course, an interesting question is, how are these emissions determined? In this region here, this is by the map, by the way, the map of Romania, with here in red and blue and green important oil and gas production sites in Romania. And the question is, of course, when we come to the emissions, do they agree, or are they true? They're using standard IPCC emission factors, but there have been basically no measurements in Romania itself. This is what we wanted to do, to find out whether this is a good target to help reduce European methane emissions. So we went out with a rather large consortium that I've mentioned already. We came from several European regions with a scientific consortium. The research was funded by the United Nations Climate and Clean Air Coalition and by EDF. We had also some interaction with political agencies, ministries in Romania. There were also the big oil and gas companies, OMV Petrom and Romgaz joined our consortium and actually provided information about the location of the sites. And we had also some non-academic partner service companies like the sniffers or scientific aviation included, that actually helped with the infrastructure and carrying out measurements. So we were quite a big group. This is only half of the group that were there with one of our research aircraft, and we carried out the measurements. I'll go back for a minute. In the first place in the southern region in 2019, and this year we actually went also to the Transylvanian gas production basin that you see here with the green reservoirs. So all these colors are proven reservoirs of fossil fuels in Romania. So what did we do? We applied several approaches to determine methane emissions. We did that on the component level, and at the component level you often use FLIR cameras or imaging cameras to detect leaks of individual components like flanges or valves and so on. We did it also together with a service company, and so we can detect leaking components, we can facilitate immediate repair and therefore also immediate emission reduction. And the cameras itself are not very good at quantifying, but you can, when you have a leaking component, you can put it in a bag and actually derive the leak rate that way. So that's on the component level. We also did measurements on the facility level, where we went to full facilities that can be an oil well or a gas well, or a larger facility with storage tanks. And we went past, we passed the plumes from these facilities here at some distance. At some point, we also released tracers like N2O and acetylene to see similar plumes of these tracers and compare that then to the emissions of methane from these facilities. And the third component is that we did basin scale emission estimates. That means that we went with aircraft around larger basins where emissions are calculated from a mass balance. That means we calculate we take the difference of the concentrations upwind and downwind of a certain region, and from that we calculate the total emissions. So very quickly, how does it look? The component level measurements, you see here an image from such a FLIR camera where you see a leak event here on top of an oil storage tank, where you really see here with the right wavelength, when you look with the right wavelength, you see methane being emitted here, and also here a little bit. You can see here one oil well where we went again on the street and we really measured a plume here of methane in red and acetylene that we released from a bottle close to this oil well. And from the ratio of these plumes here, we can calculate the emission from the entire facility when we know the release rate of acetylene. And here you see some flight profiles around a larger region where we had hundreds of individual production sites, and we measured at the upwind side and at the downwind side, or it's the other way around. This is the upwind side, and on the right is the downwind side. And you see the brighter colors are higher methane concentrations. So from the difference, we can calculate what was produced inside. In summary, we went to many of these regions. We did numerous, so at least 250 ground-based quantifications. We actually visited more than 2,000 sites in Romania where we scanned and screened for methane emissions. I told you this year we went back to the northern part of the Transylvanian Basin and did another almost 200 quantifications on the ground, and also about 1,000 screenings of sites. I should emphasize again that we work together with the operators to get the precise locations of all these emission sites. Then we went with the aircraft. We did quantifications of larger regions, as you see here, but also smaller clusters in some regions. And sometimes we also made mass balance flights, which are shown here in red. So we quantified the emissions from all these regions. And before I go to my summary, I will give you a little bit a glimpse of what we see. So these are all individual emission rate estimate that you see here. Oh, sorry, this is the wrong scale. This is actually for ethane. Let's go to this one. I think I put the wrong scale here. Let's go to this one. These are the emission rates per site. You see that they vary between some grams per hour to 100 kilograms per hour, and that's what you also see for the methane emissions. And so this is an enormous scale, and that means that we really have to sample a large fraction of the existing wells to do some statistics. And with that, I want to conclude and give some outlook on what can be done in the future. So we have established in our experiment that various methods can be used for emissions quantification in the field in our European environment here. We have also compared different techniques, and we found generally a good mutual agreement when we apply the methods at the same site at the same time. We encountered problems when we came at different times. The agreement is really worse, but also when we come at different times with the same method, we get sometimes significantly different values, which means there is often a large temporal variability, which again emphasizes that we need a large sample to cover a representative distribution of all these wells. And we quantified 400 to 500 total facilities in Romania, and more than 2,000 were screened. We do need that because we know already from our measurements and previous measurements that there is a skewed distribution. So there are super emitters, which we need to incorporate in our population. I should also say that our campaign was partly limited by reasonably bad weather for our measurements. We didn't have a lot of wind. That means that the plumes don't go in the direction where we want to measure, but they go up, and then we miss them often on the ground. So for future measurements, where possibly in the OGMP framework, companies would do that themselves or together with some service companies, they could actually also choose periods where the conditions are favorable. For example, where we have wind conditions of about 3 meters per second or larger. And I mentioned also already that our service companies are getting ready or are ready already for such routine measurements and can also support industry and policy now in helping to reduce these emissions. For our project, I have shown you some of the individual numbers. What we still need to do is to really do the statistics thoroughly and come out with an emission factor, which would be the baseline, and then also compare that to the top-down estimates that we get from the aircraft measurements. And with that, I hope I've given you some overview and insight into our project, and I'm open later for questions. Thanks a lot.
Thank you, Thomas. If there are questions, please put in a chat or on question and answer to Thomas. I would just use one question, Thomas. How much Romanian authorities have been interested? How much it will influence the assumption and the inventories of methane emissions? Or is there correlation what you have done and some impact on estimation of methane emissions in Romania?
I have been surprised, Andris, how much interest there was. So several times we talked to the ministries. The ministries actually also facilitated the companies to really cooperate. That means there was also a little bit of pressure, if I understand correctly, to make the companies cooperate. The ministries are really interested in our results. We now have a request again to open some results to the parliament in Romania so that they can be used also for the future strategies. So there's really quite a lot of interest. Sometimes the interest is even faster than we can deliver because we want to do thorough work. We want to be sure before we actually make information public, because we know it is sensitive information. But it's quite amazing how much interest there is from different parties. And I must say, not only from the policy, but also from the operators themselves. They also really want to know how they are doing and how they can improve the emissions. So this is actually a really good news. And I think it is related to this public climate on, we all want and need and have to contribute to reducing these emissions, which we are seeing at the moment.
Yes, I already got one question from Daniel Madar, SP Interface. What is the percentage of NG emitted to the atmosphere from what is produced? But I think it's more general. It's not so much for your project, or could you make an estimate?
Yeah, that I cannot really come up with a number yet, because this is what we are still struggling with, to get a statistically robust number. But this is something that we really want to find out. We have seen, and that's why what it makes so difficult, that the emission rate has rather poor correlation with the production rate. So the question is how to scale up the measurements when we know sometimes we have facilities with a very large production but small emission, and sometimes we have facilities with a low production and very large emission. So it also has to do with the state, and this, well, when you are in Romania, you can see it with your eyes. You can basically already guess whether a certain facility will leak, because they are very new, shiny, well-maintained facilities, and there are older ones, and you can really tell from the difference. And we also see that in our in our measurements, and that is one facility. But to give this now really a scientifically robust number, I think we are almost there, but I would like to ask for a bit more patience until these results will be communicated.
Thank you very much, Thomas. I have a good news now, and thank you, Thomas, for jumping in so that we can move to our keynote speaker. But Thomas, was a great, fantastic presentation, and very also promising. For Vaishali has joined us. So Vaishali, I already have made introduced you to audience. So and the main definitely is that you have been a coordinating lead author on the chapter on short-lived climate forces. So I will give the floor immediately to you.
Thank you so much, Professor Piebalgs. I will just share my screen. Do you see my presentation?
Yes, we do.
Okay, so it is in the presentation mode, right?
Not yet. No, it's not in the presentation mode. We see the slides, but we see your screen, but it's not yet in presentation mode.
Okay, let me try this again.
Yeah. Now it's
See it?
perfect. Yes.
Okay, great, thank you. And I just want to. Okay, you can see the change as well. Thank you. Okay, so first of all, my apologies. It seems like there was a misunderstanding between time changes, CET versus UTC. So I understood that as 1400 UTC. Again, thank you so much for inviting me to present to this forum. So the IPCC Working Group 1 reports beginning right from the first report published in 1990 have considered the effects of methane, aerosols, and ozone on climate. And in AR6, a full chapter is dedicated to chemical compounds with short lifetimes acting on climate. So I wanted to share with you, or start by sharing with you, the definition of short-lived climate forces adopted in this report. The report defines SLCFs as a set of chemically and physically reactive compounds with atmospheric lifetimes typically shorter than 2 decades. And by this definition, methane is a SLCF. SLCF abundances are highly heterogeneous spatially, although some can be well mixed, such as methane and some halocarbons. They can influence the climate directly and or indirectly. And so, for example, methane affects climate directly because of its greenhouse gas effect, but also indirectly via its contribution to the formation of ozone, which is a greenhouse gas. And I'll come back to this point again a little later in the presentation. SLCFs can also be emitted directly from various anthropogenic and natural sources and are formed in the atmosphere. Many SLCFs are also pollutants with detrimental effects on human health and ecosystems. The report shed light on how SLCFs are changing in the atmosphere. Insights from satellite and surface observations provide evidence that over the last decade, strong shifts in the geographical distribution of emissions have led to changes in atmospheric abundances of highly variable SLCFs, specifically ozone, aerosols, and their precursors. Regarding methane, the report finds that the methane concentrations continued to increase over the last decade. And this increase was faster over the 2014 to 2019 period. The plot here shows the trajectory of atmospheric methane based on direct measurements from various networks since 1979 to 2019. There have been marked changes in the growth rate of methane over this period of these direct observations, with a decreasing rate from the late 1970s through the late 1990s, very little change from 1999 to 2006, and resumed increases since 2006. These atmospheric methane fluctuations result from complex variations of sources and sinks, and the report assessed that the multi-decadal growth in atmospheric methane.
Vaishali, sorry, could I? We see only the first slide. We have if you have changed the slide, yeah. Now it's perfect. Yeah. Now.
I'm so sorry.
Yeah.
Right. So these atmospheric methane fluctuations result from complex variations in sources and sinks, and the report assessed that the multi-decadal growth rate in atmospheric methane is dominated by anthropogenic activities, with the growth since 2007 largely driven by emissions from fossil fuels and agriculture, dominated by livestock sectors. The figure here shows methane sources and sinks from top-down estimates for 4 decades, along with the budget imbalance, that is source minus sink in the blue bar. The black line shows the atmospheric methane concentrations from one global network. The report finds that between the decades of 2000 to 2009 and 2008 to 2017, both emissions and sinks of methane increased, but emissions increased more strongly, which implies that the emissions of methane play a more dominant role in driving recent methane increases. Natural emissions remained relatively unchanged between these 2 decades, as you see in the green bars. Evidence from isotopic composition, observations, and inventory data suggests that concurrent emission changes from both fossil fuels and agriculture are playing roles in the resumed methane growth since 2007. Accounting for changes in atmospheric concentrations and emissions and updates to forcing efficiencies have led to increased understanding and quantification of the contribution of methane to human-induced warming. This figure here shows the effective radiative forcing, which is a measure of the change in the radiative balance of the Earth from changes in emissions of individual components from pre-industrial to present day. So here in the box, changes in methane emissions not only lead to changes in its own concentration, but also affect ozone, stratospheric water vapor, halocarbons, aerosols, and CO2, and forcing from each of these effects are on a better scientific footing in AR6 compared with AR5. And this quantification of the effective radiative forcing for methane and for other compounds provides a strong foundation for the estimate of global surface temperature change from pre-industrial to present day changes in the emissions. And for methane emissions, the pre-industrial to present day changes have led to a warming of about 0.5 degrees Celsius, which is half of the human-induced warming. However, there seems to be a confusion that I've seen in the media. So the methane emission changes are basically because of just the attribution is basically because of just individual emission changes, whereas the net change in methane forcing and its climate impact is not only because of methane changes, but also because of all the other individual species. For example, as NOx changes, they impact methane lifetime and have a counterbalancing effect. So the net change from methane concentration changes from pre-industrial to present day on surface temperature has been about 0.3 degrees Celsius, which means that methane has contributed to about 25% warming from in the human-induced warming. Finally, the point that I wanted to also stress is that the report finds that strong, rapid, and sustained reductions in methane emissions would limit the warming effect resulting from declining aerosol pollution and improve air quality by reducing global surface ozone. And this conclusion is based on the assessment of published scientific literature on the role of methane in limiting future climate change, as well as the analysis of results based on the 5 illustrative SSP scenarios, the shared socioeconomic pathway scenarios, which span a wide range in the anthropogenic emission futures, depending on the socioeconomic assumptions, levels of climate change mitigation, and for aerosols, non-methane ozone precursors, air pollution controls as well. So what this figure shows is the air pollution and global surface temperature consequences in 2040 compared to 2019, and in 2100 compared to 2019 in the SSP scenarios, plus 2 additional sensitivity scenarios with varying levels of methane and non-methane SLCFs. In these scenarios, assumed simultaneous changes in methane, aerosol, and ozone precursor emissions that also contribute to air pollution lead to a net global surface warming in the near and long term. In the long term, this net warming is lower in scenarios assuming air pollution controls combined with strong and sustained methane emission reductions, as illustrated in the low and very low scenarios and the sensitivity scenarios shown in the box over here. Because of this, and this is because assumed reductions in anthropogenic aerosol emissions lead to a net warming, while reductions in methane and other ozone precursors emissions lead to a net cooling. And because of the short lifetime of both methane and aerosols, these climate effects partially counterbalance each other, And further, reductions in methane emissions also contribute to improved air quality by reducing global surface ozone. And with that, I will leave you with this summary of my presentation here. Thank you so much for your attention and your time.
Yeah, I'm waiting for others also to put questions, but I definitely have, Dr. Naik, one question, because you clearly say the methane concentration continues to increase over the last decade. That is very clear statement. Now there is a global methane pledge and there is political commitment to come down. What advice would you give policymakers if they would ask you, well, what attention to take? Because definitely we all applaud, but we would like also that there would be deliveries. That assessment report comes and says, well, the goal has been achieved with some some error, we could clearly say that we are on track on this political pledge. What advice would you give policymakers?
So I would say that based on the science and what is really important is the continued monitoring of atmospheric methane and also scientifically based estimates of methane emissions. It is really important for the science to keep progressing to show with the monitoring in methane that indeed the pledges are working, and as policymakers, following what is happening in the science arena definitely becomes much more important from my perspective.
Great. What is missing pieces when you have been lead author and contributed for all existing literature, and where did you see the biggest gaps, where you would say we need so much data, more data on it? We have now today, we have had very excellent presentation from Dr. Röckmann about the emissions in Romania they did. There is also something done in Australia. What you would need more to have more precise assessment of methane emissions?
So based on the report itself, the report has highlighted the mismatch between top-down and bottom-up methane emissions, and large uncertainties within each of these estimates. And I think from that perspective, that is a major gap, that the top-down and bottom-up estimates of methane emissions still diverge. I think they need to converge to be then able to make or confirm that the policies are working to reduce methane emissions. So in that sense, continued monitoring, better estimates of the activity and data that feeds into bottom-up estimates of methane emissions. I think it's very necessary to bridge the gap between the diverse bottom-up and top-down estimates of methane emissions.
And my third question is related for more political nature. So it is what I have seen, at least in Europe. There is some, I would say, arrogance towards methane emission promoters. People say, well, it's not so important. We are anyhow leaving gas out, or oil is going down. So we should not focus so much on methane emissions because, it's not a big issue. So it's actually could slow down energy transition, everything else. What is your impression, and what arguments you would give to me really to defend the lines that methane emissions mitigation is not secondary issues, that it's really crucial issues that can't be neglected?
So I, again, as an IPCC author, and also just based on the report itself, the report says every bit of warming counts. And therefore, methane has a role in in limiting climate change. And as you see, methane concentrations are increasing and continue to increase even up to this day, which indeed tells us that the climate effect of methane is not going away. So every effort to limit warming, not just of course, CO2 remains the big dominant forcer that we need to reduce, and of course, given its long-term effects on climate change, the focus, of course, remains on CO2, but additional components, and especially methane in this case, do have a significant role to play.
Thank you. I have two questions from the audience. Oh no, now more questions. One is just a reminder from Philip. He says, this increase was faster over 2014-2019. Could you please say why you think, or why it was so?
So based on the report, so the report basically looked at the change or the growth since 2007, but did not address specifically for the 2014-2019, and I think partly that had to do with the data set that we were working with. It seems like newer papers that have come out have highlighted the role of fossil fuels and agriculture, but at the moment, I would say that I haven't really looked at the recent literature in more detail to be able to give you a specific answer.
Okay, good. There is a very tricky question that comes up more for the future. As you know, a lot of countries are moving towards hydrogen, and Carlos Moreno Carrero asks, is there any research lines for following the potential effects on hydrogen emissions? This is something that I hear here and there the questions, and as you are specialist for pollution, so could we talk of risk of having hydrogen pollution? Yeah.
Right. That's a great question. And yes, indeed, there are studies happening as we speak, where scientists are looking at the effect of increased hydrogen emissions, either through leakages, how that would affect climate and air pollution levels, specifically climate via its influence on the methane sink, and pollution via, again, its effects on methane. So in the science circle, there are Earth system models are being applied to look at these effects of hydrogen, and in fact, some of the studies have already quantified the potential, the warming potential for methane. So as more studies come forward, I'm sure these studies will be assessed going forward and highlighted the effect of hydrogen.
Thank you, Dr. Naik. It was really great having you, and thank you for joining us, and sorry for Europe. I am based in Riga. That is also sometimes making my life miserable because it's East European time, not Central European time. So we will be very privileged to have you, and much appreciated. And thank you for sterling work you have done on AR6. So, and good luck with your other projects.
Thank you so much.
Now we will move on the project of Bryce Kelly from University of New South Wales. He's a PhD, he has PhD in environmental geophysics. He is leading the research on evaluating the impact of coal seam gas and coal mining on groundwater and air. And recently they have made extensive measurement on the major greenhouse gas emissions throughout New South Wales and Queensland. So as the time of difference with Australia also is quite significant. So we have made registration his statement and his presentation. So if I could ask my colleagues to put it on screen.
Welcome to this presentation on baselining coal seam gas methane emissions in the Surat Basin, Queensland, Australia. I want to thank the Florence School of Regulation and the Environmental Defence Fund for asking me to present today. My name is Bryce Kelly. I'm Associate Professor of Earth and Environmental Science at the University of New South Wales. I'm representing my colleagues here, all listed on the right-hand side of this slide. This team delivered on the first assessment anywhere in the world of quantifying the emissions from coal seam gas developments using airborne measurements. Last week, the Australian government announced that at least one new basin will need to be brought online before 2030 to meet the projected East Coast gas demand. But they also stated that it was critical to unlock by 2030 4 new gas developments in the Narrabri Gas Project region, the Beetaloo Sub-Basin, the Galilee Basin, and the North Bowen Basin. To support all this additional gas production, they want to expand the capacity of the existing pipelines, and they also need to install thousands of kilometres of new pipelines. All of this development will add to the methane emissions from Australia. The Surat Basin is one of the largest coal seam gas developments in the world. Our study area extends northwest of Toowoomba and covers an area of approximately 200 kilometres by 200 kilometres, 0.5% of the surface area of Australia. But our calculations show that this region accounts for 3 to 4% of Australia's methane emissions. It is anticipated that when the region is fully developed, that there'll be 20,000 coal seam gas wells and supporting infrastructure in the region. In 2018, the total gas produced in the study inventory domain was 21,500 million metres cubed from 3,400 coal seam gas wells. In Australia, facility greenhouse gas emission data are not in the public domain. At the beginning of our study, we thought we'd use the Catestone inventory. It was calculated for a joint study between Catestone and CSIRO for JCERA. Catestone constructed a bottom-up inventory for the year 2015. This inventory was used as the prior for the CSIRO two-tower regional basin inversion, and the tower positions are shown here in the figure at the top. Catestone used the American Petroleum Institute methods, but not all calculations were transparent. They did not use the IPCC or Australian Government emission factor for grazing cattle. They used a value that was 30 kilograms per animal per year higher than normal. The Catestone production normalised emission rate is only 0.14%. This is low by international standards. In the subdomain covering the coal seam gas developments, the CSIRO inferred emissions are 33% higher than those of the Catestone inventory. So given all the above, we decided to build our own inventory for the region. There are 3 components to our study. We calculated our own inventory using the Australian government workflow as they use when doing the national accounts for the UNFCCC reporting. We did our airborne measurements, and I'll talk about those in more details in the next slides. We also analysed the plume chemistry and analysed the isotopic composition, and this portion of the study is still ongoing. This image is an airborne view of the coal seam gas field. Each square represents a cleared zone around a wellhead, and then we have all the lines of the pipelines connecting through to the compressor stations and then the processing plants. Here we see an airborne photograph of one of the major facilities, There are 38 major gathering and boosting stations and processing plants in our region of study. There are 55 feedlots in the region, holding up to 500,000 cattle. The largest feedlot, at the time of surveying, had a capacity of 70,000 animals. Also in the region are 1.8 million grazing cattle. So you can see that the cattle are a major source of emissions in the region. Many of these feedlots are co-located with the coal seam gas developments because they're using the co-produced water, which has been treated and then provided to the feedlots for usage. This image shows the results of a mobile survey where we had a car-mounted greenhouse gas analyzer, and you can see that we mapped out river seeps, coal seam gas plants, the emissions from feedlots, the emissions from the coal mines, the raw water ponds, which are holding the co-produced water from the coal seam gas. There's compressor station emissions, raw sewage plants. All these plumes are very closely located to each other. The image on the left of the slide is showing the distribution of the 4,000 plus coal seam gas wells, and the image on the right is showing the individual point sources, and there are over 300 individual point sources. And there's a listing here on the right hand side that shows all the different categories that we had to consider. There are many diffuse sources of emissions that we also took into account: grazing cattle, kangaroos in the forested area. There are emissions from the irrigation district, and there are also emissions associated with natural seeps along the Condamine River. Within the domain of the airborne survey, the major source of emission was the coal seam gas. That was followed by feedlots. Then we have the grazing cattle, piggeries, coal mining, and then all other sources were only a tiny contributor. All of the airborne surveys were done using a demoner. We did 13 science flights over 15 days. Most of the flights were 150 or 300 meters above the ground. Each flight line was done at a constant height, and the cruise speed was around 150 to 170 kilometers per hour. The analyzer was mounted in a pod on the wing so that there was no contamination from any of the aircraft emissions, and the image on the right hand side here shows each of the flight lines. They were designed with consideration of the prevailing weather conditions and the objectives of measuring upwind and downwind of sources of interest. Here we have a schematic representation of our surveying. We have an upwind flight, we have all our sources within our convective boundary layer, and then we have a downwind flight. And we're determining the mass balance of the difference between the ins and the outs. Here we have one flight line set, the upwind and then downwind, and then this downwind becomes an upwind, and then we have another downwind, and along each of these bands is the emissions between the upwind and the downwind. We determine the mass balance in each of these zones, and there are 32 zones. In this graph, we're comparing the top-down estimates from our surveying versus the inventories. We have the UNSW inventory, which is blue, and we have the Catestone inventory that is in orange. And this is our one-to-one line. For the majority of our 32 zones, the UNSW and top-down measurements were agreeing quite well. We did not get that match with the Catestone inventory. If we look at this in the one-to-one plot, you can see the distribution once again between the UNSW and the Catestone results. Here we compare three inventories for the regions. There's the Catestone, there's Capelli, which is based off the UNFCCC reporting for 2016, and then we have the UNSW inventory for 2018. The UNSW inventory uses the latest Australian government guidelines for calculating emissions for a region, and you can see that there's good match between the UNSW inventory and the top-down measurements within the uncertainty of the top-down measurements. Using the UNSW inventory, we then have a look at the coal seam gas production normalized emission rate, and it's 0.37% from the UNSW inventory. This is in contrast to the Capestone inventory, which is only 0.14%. On this slide, we compare the Surat Basin gas production normalized emission rate with all the other top-down studies around the world. So here we see all the basins that have been studied using airborne methods. The Surat Basin is low by international standards at 0.37. This is a dry gas field, and this is also a brand new gas field recently constructed. It will be interesting to see how the emissions change through time. You have higher emissions for the wet dry gas, and then the highest emissions for all the wet gas fields around the world. After MethaneSat is launched, we hope to go back and do a study where we have the continuous observations from the satellite, we have a new snapshot from the airborne survey, and we'll be comparing that against an updated inventory. Thank you to all the sponsors of this research. It's clearly having impact in Australia, and I also get many inquiries from around the world. If you have any questions, feel free to send me an email at the address below. It is my understanding that Thomas and Stefan are now waiting for your questions associated with this presentation today. I hope you have found it informative, and thank you and goodbye.
Well, very, very interesting presentation. Unfortunately, Bruce Kelly could not join us. Is there anybody who would, to raise any question? But that perhaps I could ask Thomas, what if you compare what Bruce's opportunities and what you have had in Romania, would you see considerable difference in approaches, or you would see that there was some elements that you would like very much also to do in the potential next studies in Romania?
Yeah, thanks a lot. Thanks also to Bryce for the nice presentation. Yeah, he presented it in some more detail than I did, so that's nice, because indeed many of the elements are the same. Are similar. So they also did ground-based measurement. They probably focused a bit more on the aircraft-based measurement. So this is something that, well, of course, requires a certain infrastructure. For us, the aircraft measurements were limited. The other difference is that Bryce had the opportunity to do the research over a longer time period. We had a relatively short time period where we really needed to be there with all the people to finish the study. So I think that has a couple of disadvantages. One is, of course, that you're only capturing the emissions during a certain part of the year, and there may be sometimes also meteorological conditions and other conditions related to the operation of the structures that have an effect. So we would like to actually make this more often, and I hope that new proposals will also get funded to go back and also see how the emissions evolve. First of all, during the present time, but then also when the operators hopefully try to improve the infrastructure and reduce emissions in the next years. I think that would be one of the very important steps when we are now talking about the baseline, but what comes after the baseline, right? Then you want to be able to compare that compared to this baseline's emission have actually changed, ideally, of course, gone down. And that means that we need to establish this baseline, that's important, but also we need to go there regularly to check whether the promise or the emission reductions that are hopefully reported on paper, whether they actually occur. And I think that's one thing that we should always keep in mind, that you can report easily things on paper, and there are also some examples where emissions go down because of some changes in calculations, but actually the emissions have not changed at all, but the calculation methods have changed. So we need to have a ground or a ground truth or an air truth, I would say, to make sure that we can really quantify these emissions and also monitor this over time. So that's, from my perspective, what is crucial. And then the other aspect is also that we hopefully try to empower also the operators themselves to contribute to these kind of emission rate estimates in this OGMP infrastructure that is being built up, or that has been built up already. I hope that answers your question.
Yes, it does. Could I ask also a speculative question? I believe in the process to 2030, the questions, skeptical questions, does government are just diluting blah, 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 as one very famous fighter for limiting climate change says, how much credibility will be in government actions on reaching on global methane pledge? Is this methods that we use today robust enough to be credible, saying, well, we did this and that provided the result? Or there will be big uncertainty around the baseline that would compromise whatever governments would say? My point is basically how to create credibility in actions. That's what I say. Because there will be one group of people that would say, just stop using fossil fuels. That's our point of departure, whatever happens. And it will never be majority. So very difficult to expect that it will be followed. But it's also painful to hear like what Greta was saying, because in a way, there should be credible middle way to deliver. There will be somebody who would say deliver too much, somebody would say deliver not enough, but at least there will be the process that is more to consensus building, not separating us as a global community.
I think it's a very good question. I think you can say, is it now enough or not? That's another question, right? But is it reliable? If someone says we have reduced emissions by 20-30%, will that be credible? Will people believe us? And therefore, well, we need to really come, I think that's part of this workshop here, we need to really come to methods and to scientific procedures that are accepted, that are also well documented, that have well described error margins, because the errors are also important. As scientists, we are used to that, but in the end, when you communicate it, the errors are often forgotten. So if we now make another study in Romania in 5 years, will we agree, have the emissions been reduced? That also needs to be considered under the error that we are having, right? And it means also that we really also need measurements that help us establish this baseline. So it's really important that these measurements take place now, in the near future, so that we are actually able to compare. If there's no data now, then we will have no way of verifying that any reductions have been taken place. And that is what is happening at the moment, also even in the official EU reported numbers of emissions from oil and gas sector from different countries. There are sometimes jumps that just happen from one year to the other. They are in the official numbers, and there are even sentences saying that the EU reduced emissions here in this sector, where it is very obvious that nothing was changed, but just the numbers were changed. And this is something that also needs to have some attention. I expect that this new International Methane Emissions Observatory, IMEO, of the UNEP will really also establish rules and baselines for how this reporting is happening.
I think very clear action should be supported by robust measurement data. So that's not just reporting. Yeah, yes, that's good. I saw that Ricardo rose his hand. Ricardo, the floor is yours.
Yeah, thank you very much, Andris. Can you hear me?
Yes, we do.
Perfect. I think that the previous speaker has pointed out something important, which is the uncertainty ranges in the estimations. This is probably not so important for the general public, because typically, okay, I do not say that the general public do not understand if you tell them 134 plus minus 4 or minus 3 plus 5, but probably it will not be so easily understandable. But for the scientific community and for the policymakers, it is really important to understand, and also to see if any change that takes place over time is significant, statistically significant or not. Because sometimes we are looking at reductions that reductions in emissions of CO2 and of methane, that if we look at the uncertainty ranges, probably eventually the statement that we can say is, yeah, the best estimate indicates some reduction, but we don't know if the reduction is true or not, because the uncertainty in our measurements, the uncertainty in our data do not allow us to make such a statement. So our best estimate indicates so, but there is no evidence, no real statistical evidence that the reduction is really true. So what I would like to convey, the message that I would like to convey is the need to really deploy the right statistical methods associated to the measurements, so that these uncertainty ranges are, let's say, are theoretically well supported and can be used to really understand if the changes that we will see over time are significant or not. Yeah, thank you very much.
Thank you, Ricardo. I would like to thank again Dr. Naik, Professor Röckmann, Dr. Kelly for fantastic presentations, and it was really, really eye-opener, I think, in many respects. But the good news, that is, at least for Professor Röckmann, reports that at least in Romania, there is a response. Also in Bryce Kelly report, also authorities really take care about the research being done. And we could move now to the second session. It's very much connected to the first. It's key areas for further report. And I'm very glad that Steve Hamburg, chief scientist at the EDF, joined us and could make his introduction to this part of it. Who do not know Steve, I think in this audience, most probably everybody, but he's also working with IMEO, scientific leader of scientific committee, and also he's on implementation committee. So we have a good chance, as Professor Röckmann mentioned, that IMEO will be on the right track. And he is also EPA's scientific advisory board, so that US ambition will very much support him by scientific advice. So I could continue about Steve's biography to speak a lot, but I promised him that he will definitely have enough time to say on this topic, on the further research that we need really to proceed with. Steve, the floor is yours.
Thank you so much, Andris, and it's great to be here. And I couldn't have asked for a better set of talks to set up my comments about the International Methane Emissions Observatory that was just referenced, IMEO. The vision for IMEO is exactly to fill the conversation that we just talked about, to provide the high quality data that we need to be able to understand both where emissions are coming from, how much is being emitted, and how it's changing over time. And so that's the goal for IMEO. It's to be honest broker. It's not to set agendas for how we'll meet the pledges and other commitments of countries, but to provide that data in a way that really allows us to understand the emission patterns to a level that we've never been able to do before. And in order to do that, we need to really be, as it was said, is really scientifically based and bring that data together. So to do that, we're talking about bringing together basically 4 streams of data that currently exist. So we have these self-reported, and we're going to start with fossil fuel, methane emissions from fossil fuels, but then move on to other domains so that we really can talk about human emissions across the board. Within the fossil fuel domain, the Oil and Gas Methane Partnership 2.0 is providing 70 plus companies are providing voluntary data that on their emissions with an explicit requirement of increasing the quality of that data to include empirical observations and top-down, bottom-up validations. So that data set is part of what will be used. Additional remote sensing, there was some questions about and comments about using remote sensing techniques, using satellites, which are growing ever better and will be over the next couple of years with the existing planned launches, of which one I'm involved with, which is MethaneSat. And then also the science studies we just heard about, Romeo and the work in the Surat Basin, bringing those data together. And then we've also heard about inventories. Well, we really need to bring all of that data together. And one of the things that we just heard some about is, depending on how you look at the problem, the issues in front of us, it can look quite different. And the image and metaphors are always problematic, is if we're looking at an elephant from the rear end or the front end, they look quite different. They're the same elephant. And what we really need to do is describe the entirety of the problem, understand where those tensions exist and where they don't. And often we imply or we perceive tension in the data, and it's simply because we're looking at the problem from a different perspective. And I think, as we heard in the two examples of the case studies, one is generally able to resolve these multiple perspectives, but it does take some work. And that's what we'll be doing at IMEO, is really bringing those approaches together in an automated way. The issue came up on reconciling top-down and bottom-up. Currently, we don't have good reconciliation because we haven't brought enough data together. In all of the examples that I'm aware of, we've been able to resolve the top-down and the bottom-up by integrating multiple data sources. And I'm optimistic that as we do this on a global scale, this will be possible. And I'll just talk about some of the data streams that are already happening. OGMP, the Oil and Gas Methane Partnership 2.0 data, is already being provided. It's required to get better over time. We have the European Space Agency satellite TRPOMI, the Sentinel-5P data, that's already being publicly available. And the analytics company Kairos will be providing all of their data products into IMEO. Additionally, someone had raised in the chat, GHGSat, a Canadian satellite that looks at methane. They'll be providing all their data with collaboration of the Canadian government to IMEO. We have the new satellites, as I described, that'll be coming online. And that data, all of the MethaneSat data that we generate starting in 2023 will be part of IMEO and at no charge. So we have those different multiple satellites. We also have the studies that we heard about 2 of them, but there are many more studies that are been sponsored by the Climate and Clean Air Coalition work over the last 5 years and will be continued to be sponsored by IMEO. And then we, of course, have the inventory work around the world. So we have very specific streams of data, and we'll be able to use those streams to craft an integrated picture, which will be key to taking action. If the goal of this effort is to do good, high quality science, the goal is to ensure that we're honest brokers, that where there are tensions in the data, we acknowledge them. There are places where we won't have agreement. But I do think that based on our past experience over the last decade, that those will be relatively few. And we have an opportunity with methane to lead the way on greenhouse gases in just a couple years of producing high quality understanding. And then the last point I'd like to make is this issue of change over time. I think it is a critically important thing to be able to do. And it's not quite as hard as we perceive, because up till now, we've been taking snapshots with very limited, as we heard, we can only afford to take measurements at a limited period of time. So it's very hard because of statistical uncertainty in each of those to be able to see change. With remote sensing and much better remote sensing, where we're getting snapshots, it's more like a movie. Constantly taking them, we can see change over time. And recently that has been demonstrated in the Permian Basin, where we've been able to demonstrate quantitatively, statistically, the changes in emissions associated with economic activity, with the COVID downturn, the price downturn, and we actually can map that over time. I believe we'll be able to do that on a global scale within just a few years, and we'll really be able to understand where those emissions are coming from, who's emitting them, and how they're changing. Thank you very much.
Thank you, Steve, for this very optimistic forecast. And I think it would be great because I recently also have been engaged in some debates about the EU greenhouse gas mitigation policies, and some people say, well, you have had crisis after crisis, what do you expect? So, and I think it's important really to have very credible movie, as you say. So what is happening? Yes, there is a crisis, but still you see the pattern. So I think that's great if we are looking in this direction, and let's hope that we will manage it sooner than later. I see from Daniel SP interface to it's not a question, but I assume there is a question, Steve. If you could look on chat, what he says, the data I know of is that 150 TG methane is emitted from oil and gas annually, mostly from gas, and 90 TG methane from agriculture. It's not a question. Basically, if I could extrapolate this, what I assume Daniel is trying to say, I know enough. So I
don't actually think those numbers are accurate. I'd like to know where he's getting them from, but we don't. We have a large uncertainty right now in the oil and gas inventory emissions. We know that because we don't have empirical data from much of the world. That's where satellites will be critical. The satellite data is emerging almost daily. The analysis is still pretty complicated. It's being automated, where we'll be able to get much more direct data. Agriculture is a large emitter, and that's reality, as was talked about. Enteric fermentation, waste, rice produce a lot of methane. It's not a competition. All methane was created equal. We have to reduce all methane. And the good news for oil and gas is that there's lots of evidence, and we saw that we have the technology to radically reduce those methane emissions, and we can do it quickly, and we can do it at a large percentage at low cost, as the International Energy Agency has shown in a recent report that reaffirms what had been previously talked about, and that we have to do it faster than the rate of decarbonization, because we can reduce methane rapidly enough to actually slow the rate of warming while we're rapidly decarbonizing. And the difference between that timeline really matters in terms of driving the rate of increase in warming down significantly.
Thank you, Steve. There is a question. Is there a platform where operators, regulators, and auditors can meet to kick off methane emissions monitoring projects together? So,
well, the OGMP 2.0 is exactly designed to do that, is to create a forum for that. There are also, of course, industry efforts to do that. And I'm not up on all the industry ones. I know in the US, there's a group called One Future, and I know that the international, I'm bad with acronyms, I can't do it off the top of my IPCA. There are different forums. The key is to recognize that empirical data is essential, because these emission factors, as I think Thomas talked about, sometimes they get changed for various reasons, and you have a perception of a change in emissions when in fact it's a calculation change. And while it's important to use the best calculations you can, we can't over-interpret those. And so there's been a lot of interpretation of changes over time that are purely a function of arithmetic and not necessarily a reflection of the real world. And so that's where empirical data is critical. We know that most of the emission factors do not include a good characterization statistical. The point was made earlier by Ricardo of making good statistics. Well, we know the distributions are not normal. These calculations generally assume a normal distribution, and it's simply not true. It's not representative of the real world. So you need to have empirical data to get a proper distribution so that you can apply your scaling factors with any kind of precision and confidence.
Steve, that was brilliant presentation. It's very clear messages and answers. If I now can move to Manon Simone, she's from Carbon Limit. She's consultant, and they are consulting in the identification and development of emission reduction opportunities. Also, Manon has studied both in Norway and Belgium, so it's I would say, good mix for this. And she specializes in energy, climate, and environment, and works on projects also related to methane emissions along the oil and gas value chain. Manon, the floor is yours.
Thanks a lot, Andris. So yes, as Andris just mentioned, with carbon limits, we work on various aspects of methane emissions in the oil and gas sector specifically. And we sort of see how we can work with these aspects to see how to mitigate emissions. But of course, to reduce emissions, it needs to be reduced compared to something. And this is where setting a right baseline within the current challenges, how we can put that together. Yes, here we are. So the main question here is, what constitutes a good baseline, and why aren't good baselines already in place everywhere? Setting up a good baseline isn't just as easy as that. So there are 5 main factors that need to be taken into account. It won't necessarily make a perfect baseline, but looking into these 5 elements already is a good start. So the first element is to have in place a set of robust activity data. So that means knowing how many facilities, how many equipment or components you need to report on. This might sound easy, but in some areas of the world, for example, oil production is still confidential information. So having in place this activity data is not necessarily a given. So then the question more is, of course, if we want to go beyond just this throughput data, is how to develop a robust sampling. You probably won't ask companies in a certain jurisdiction to look into sort of counting each and every one of their connectors or each and every one of their valves. It'll probably be more interesting for them to know per facility or per equipment how many of these components they have. So for that, they need to know how to sample it, how to develop these activity factors that will let them know how much activity data they actually have. So this has actually occurred already in some areas of the world, but it's not necessarily applicable everywhere else. And so this is work that needs to happen, because depending on different operating practices or climate or different even providers, these numbers might be very different. And so it's the question of knowing what are the key parameters which will influence this value for activity data, and how does it vary across different jurisdictions. And then something to sort of help here would be not looking directly at emissions, but actually using satellite technology and artificial intelligence to determine these numbers in a different way without having to go through the old-fashioned PNID count. Then once you know what your activity data is, it's important for a good baseline to have some robust emission factors. Typically, these are measurement-based emission factors so that they take into account, let's say, the full distribution of emissions. As we've discussed a lot today and mentioned a lot, is the presence of super emitters, which come in later on, but already sort of implied in the emission factors to make sure that the full distribution of emissions is included. So both from the large number of small emission points up to maybe the few larger emission points. How can these be reflected in the emission factors? And then what's important, as we know, methane emissions are very variable, and it's to understand what drives this variability to also help reduce the sample size that is necessary to determine the robust emission factors, and to make sure that not everything needs to be measured just sufficiently so that we can have a good sense of what the baseline is. This could be, for example, if you have compressors, you have some that are from model A and some that are from model B, and both of them have very different emissions. And if you just look at compressors in general, you might have a very wide variation, but if you look at Model A and Model B, they'll be within a similar range. Then another important aspect to take into account for the baseline is, of course, the presence of super emitters. If these aren't taken into account, then there is a high risk of completely underestimating the emissions that are then reported as the baseline. So there has been more and more work happening now on these super emitters or super events, and it's to see how this work can be leveraged and put into practice for the specific jurisdiction where a baseline is being established. So then it's sort of better understanding these super events. A lot of work has been done, as I mentioned, but also being able to understand what drives these events, why do they happen, and how often do they happen. It allows to identify them better and to include them better in the baseline, make sure that they're fully captured. The next important point is that the baseline needs to be able to show how to prioritize efforts and also track progress. To prioritize efforts, and this is an important point, is that mitigation or emissions reduction happen at the component level or at the equipment level. Knowing the emissions for a full facility is essential to know where to sort of prioritize efforts, but the real mitigation happens at the component level. And so here, something to work on to have a good baseline is how to combine both these bottom-up and top-down estimates. So we know where the emissions happen, how large they are, how do we then see where we need to work? And this needs to be included from the start in the baseline, since the end goal is actually to mitigate. And then a final point for developing a baseline is that it needs to be sort of reasonably developed within the time frame and resources that are available to either any governing body or any kind of initiative. A lot of work has been done in some areas of the world to establish a good baseline, to have some good sense of emissions for that area specifically. But unfortunately, not all areas of the world have access to the same resources. And when I say resources, I don't just mean financial resources. In some cases, it can be the knowledge or human resources that are not necessarily available in that area to help develop these baselines. So since the work has already happened, there's definitely some lessons learned and some shortcuts on which countries can build on, which can help, but a baseline, it's not possible to just copy paste from one area to the other. There are very different operating practices. There are very different nature of facilities, for example, or even of climate aspects in a certain region. And so it's to understand what can be reused in a smart way to sort of optimize the resources that are available. Some countries have access to universities, can fund these universities or other research bodies, but it's not the case for all. So how can those who have more limited resources build on the findings of the ones that do have the resources to be able to establish a baseline in an effective way? So those are the 5 elements. This might not provide a perfect baseline, but if regulators or other international initiatives manage to actually answer these questions that are listed here, it's already, let's say, a good start and quite a bit of progress on having a good baseline that will then allow to have a starting point to look into emissions mitigation.
Thank you, Manon. I think it was a very, very clear statement. I clearly understand now what this good baseline looks like. I have not seen anybody who challenges your 5 points on it. Is there growing interest from company side or from regions about these baselines, or it is still to be expected that more political attention will be drawn to it? How do you feel the the environment in Europe or perhaps somewhere else, how things are evolving on this? Because if I would be head of any company, and I am not, I would immediately would say, well, what are our greenhouse gas emission portfolio? And we need a baseline for methane if I am working in the area of agriculture or energy, or more general CO2 if I am in other areas. So is there activities that you felt, because your lessons or your proposal is very, very clear?
I think the main challenge here is actually access to resources, and more specifically knowledge. So in some areas of the world, especially, for example, in the United States, a lot of work has been done on methane, and probably a lot more to come. Europe is also quite close there, but Europe is much less of an oil and gas producing region. So the challenge here, I think, and for companies specifically that have assets in a lot of different countries, in a lot of different jurisdictions where the rules are very different, and sometimes also have joint ventures with other local companies, it's to actually be able to establish a baseline which works, let's say, everywhere. And so they might have a very good baseline in Europe, for example, or in the United States, where they have a good sense of their operations. But in other areas of the world, they might not have the trained personnel or access to knowledge, even to the technologies, to have a good sense of their baseline and know where to start, because their assets aren't in regions where the work has been done, and so are operated very differently.
Okay, clear. So I don't hear any questions. So thank you, Manon. It was really a fantastic presentation, and I expect that there will be growing interest in this issue with new global methane pledge. But not only, I assume that now there is corporative thinking and also sustainable finance related. There's so many factors that it should be, all the difficulties should be overcome, and companies should have, well, I would say, very clear policies on these baselines. And if there is a lack of assets in somewhere, then there will be response. I see that Ricardo has raised a hand, but Ricardo, I will give also you the floor. Also, you are also one of the speakers. So our next speaker is Ricardo Balado-Levin. He works in Joint Resource Center. It's Institute for Energy and Transport. He has a very long experience in gas risk assessments, and is now moving very much to next risk assessment, very much related to the issues related to greenhouse gas emissions. Ricardo, the floor is yours. So if you would like to start with statement or comment on what Manon has said, or if it's question, you definitely are free to put the Manon question first and then to make your presentation.
Well, I think if you agree, I will go first to my presentation, and later on we can come back to Manon's presentation and proposal. Yeah. Let me see. I hope I will do it adequately. Sharing the screen. Screen one. Okay, that one is fine. Yeah. Hello. Can you see it?
Yes, we do, but it should be presentation mode, but we see your screen.
This is the, okay, let me use perhaps the PDF. The PDF could be better, because I'm afraid that if I use the presentation mode, I could lose control of PowerPoint. Just a second, let me, because I created a PDF for this. Yeah, can you see the PDF?
Yes, we do. We do. Yeah, good.
Perfect. Okay, then I will give a few notes. I will try to be fast. And you know that one of my concerns whenever dealing with this, which is also a concern in all the other presentations, is the issue of uncertainties. Then, and this is really crucial. I will speak a bit about the pervasiveness of uncertainties. We have uncertainties in all the measurements of and in all the accounting of emissions. I will give an example of flaring, particularly. We have flaring, venting, and fugitive emissions in the energy sector, but particularly of flaring. And then I will give, I will at least say what we think that could be a good option for measuring, reporting, and verification, having a good baseline. Well, I would like to stress with this presentation a couple of things. First, something that is already quite well known, which is that the global concentration of methane in the world is quite well known, so it's accurately measured, so we have a good knowledge. But the problem is when we come to the emissions. And then I have taken this table that you can see in the presentation from study of Jackson et al. From 2020, where essentially these colleagues are comparing studies done about methane emissions in the period of 2000, 2006, and 2017, and also with two types of methodologies, bottom-up and top-down. Well, I would like to stress from this slide just two things. The first one is the huge spread. So essentially here, for different sources of emissions, what is represented is, between brackets, the range of all reported values in different studies and the best estimate. And well, you can see that, for example, for other natural sources, which you have in the second line, you have in the period 2000 to 2006 a spread between 143 teragram per year and 306. So it's more than a factor 2, the spread of uncertainty that we have in the emissions. So that's one of the big problems that we have, that because of the different ways of measure, because of the different hypotheses, we have a big spread of measurements for theoretically the same emissions. And second, if you go here in this table to fossil fuels, and you go to the studies in 2017, you can see what is the spread of the bottom-up and of the top-down measurements. And you will see that in the bottom-up, you have between 121 and 164 teragram per year, and you have between 91 and 121 teragram per year. So you have two different types of estimates, and what you get is that the uncertainty ranges do not even overlap. So this is a problem. When you are measuring with different methodologies and eventually the range of measurements do not overlap, it means that essentially you are measuring different things. So we have a problem. This is probably something that you already knew, but I think that it's good to put it with numbers. So we have a problem regarding reporting because of the huge spread of values that we are reporting, and because in some cases, the different methodologies that we are using do not even overlap in the final results that they are delivering. Now I will show you something about flaring and venting, but I will focus particularly on the issue of flaring. So here you have two pieces of information. On the right, you have the emissions in the oil and gas sector reported by the International Energy Agency in 2021, and they are reporting about 2020. And you have the three sources, so incomplete flare, venting, and fugitive emissions. On the left, you have the reporting on flaring done by the Global Gas Flaring Reduction Partnership. So I would like to go first to the left. In the left, what you can see is that the blue line is giving you what is the quantity of gas that has been flared on in units of millions of cubic meters per year. So essentially, we are in the range of 150,000 cubic meters per year, which is approximately, for you to know, 1/3 of the gas demand of the European Union. So we are speaking of huge quantities that are flared according to our estimates. And you can see the black line that the production has been increasing steadily, slightly and steadily. So you can see also that between 2019 and 2020, the flared quantities have dropped from 150 BCM to 142. Well, this is the first thing that I would like you to look at. I will not get into the details of how these values are estimated because of lack of time, but essentially these are based on a regression that is using a very broad number of measurements all over the world. Well, my point is the following one. This drop from 150 to 142, I don't have the data about the uncertainty ranges, but I have seen the regression that is used for building up this. For me, this value, this decrease of 8 BCM is not statistically significant. It's really impossible that with the data that are being used for this decrease of 8 BCM, which is approximately a decrease of 5%, this is not statistically significant. And this is why it's important really to develop methods where the uncertainty ranges are clearly provided and we can really test if the increases or decreases that are being measured are really significant or not, if we are measuring a real signal or we are measuring just noise. The second thing that I would like to say here is that if you look at the right picture, the one provided by the IEA, where you can see the different emissions produced by the oil and gas sector, you will come up with a total quantity of 72 million tons of methane emitted by the oil and gas sector in 2021. And out of these 72 million tons, 3 million tons are methane slip. And the methane slip is the gas, the methane that when you want to burn it, you are not able to burn. So it would be a fraction of the blue line, of the 142 or of the 150 BCM that you are not able to burn. Then we will go to the next slide. And here you can see, typically, you can see here some data coming from experiments done on flaring. So typically, you will read in the literature that when you are using a well-designed flare, you reach an efficiency of 98% or even higher, so that only 1 or 2% of the methane is not really burned. Well, on the right, you have a study from 2001 where you can see a number of experiments, and I would like you to pay attention only to the last line, which summarizes more or less, particularly the last two values on the last line. And that is telling you that in these experiments, essentially what was reached was an efficiency in the combustion of 68 plus minus 7. So essentially, we were getting an average combustion efficiency of 68%, which means, in average, 32% methane slip. So 1/3 almost of the gas, of the methane, is not really burned, so it goes directly to the atmosphere. Then if you look at the IEA estimates, and then you compare with the values of the Global Gas Flaring Partnership, you will see that what we are getting from those values is that essentially the values that are reported correspond to a 3% methane slip, 97% efficiency, which is completely in contradiction with some of the experiments that we are getting in the literature. On the left, you can see another distribution of efficiencies where you will see that a very large fraction of the flares have a much lower efficiency than 98%. So what do I mean? I mean that we could be severely underestimating some sources of methane emissions. And this because of not assessing correctly the uncertainties in the emissions. Finally, I would like to give my advice about what we think that could be a good method for starting a line base for reporting. And this could be the OGMP 2.0 framework recently proposed just 2 years ago, if I remember correctly. And in this case, I would like really to send the message that we have to be ambitious and we have to use a tier 3 method, and particularly when we go to the methodology, to the framework OGMP 2.0, we should go to level 3, where we should be able to measure and estimate the emissions at source level and validate this with measurements at site level. This is the only way, in our view, to really get a decent baseline. And of course, this will not take just 1 year, probably it will take 2-3 years of hard work to really get this baseline. And for this, we think that we have to use all the methods, all the methodologies and all the means at hand. So we have to use airplane-based measurements, satellite-based, direct measurements, whatever we have to guarantee that we are not allowing, that we are not really reporting in a biased manner. And of course, providing the right statistical methods to quantify the uncertainty. Thank you very much for your attention. I hope I haven't exceeded too much the assigned time. And Andris, if you allow me, may I make a comment on Manon's?
Sure, because she's impatient waiting what you will be saying.
Okay, thank you very much. You know, I would like to say a few things. Well, or just perhaps just one main thing. Look, I think that what Manon is proposing, I think that should not be so difficult to achieve. And you know, I understand that we are speaking mainly on the energy sector. I hope I'm not mistaken. Well, I would like to say one thing. My experience comes mainly from the area of security of gas supply, gas networks. Then what I would like to say is that the industry has a lot of knowledge about the systems that they are managing. For example, in the European Union, you have since the 1970s an initiative that is reporting. There is an association of transmission system operators that are collecting data about failures in the gas network. So about ruptures, about pinholes, about holes. So the industry has a lot of knowledge about how their facilities leak and how their facilities work, and when they are venting and when they are leaking and why they are venting and leaking, and when they may have big events. Because if you have a big event where you have a big release, you realize that in your operational variables. So my point is the following one. If the industry feels really involved and really gets committed to implement a methodology to really measure correctly or with a very little bias and with the right uncertainties the emissions, I think that this is achievable because in general they know very well the business that they are running. They have a lot of information, and setting a baseline will take time. It will not be done in 1 year, could be 2-3 years, but I think it's feasible. Sorry if I have taken too much time.
No, I think Manon is quite satisfied what you have said, and I believe that it's true that industry has quite a lot of knowledge. but sometimes not always knowledge is transformed in action. We have really fantastic reports, and I am in this session we come to concluding remarks or concluding statement, and I'm very happy that Casey Michels, legal advisor, Office of Legal Counselor from International Energy Agency, has joined us. I think he's main person, at least at these efforts nowadays, because his regulation of methane emissions from oil and gas, I think, is studied all across the world. So, and Casey is really driving methane agenda and also helping to IEA to keep the leadership role. Casey, the floor is yours.
Thank you for that introduction, and thank you also for these earlier comments from folks. I found this really interesting. I just wanted to add one brief comment on the incomplete flares that Ricardo was just speaking about. So one of the things is that our estimates of flaring depend country by country, so they're not precisely the same for each country, but in fact, our global estimate for total flaring from our models is a bit lower than the GGFR number. But when we look at this as a global average, we estimate about 8% of gas intended for flares is not combusted. So our methane slip number is a bit higher than that. It's about 8%. But I think the point on uncertainties is very well taken. And in fact, it's one that's really relevant to the discussion today. And we've also been encouraging more studies on this exact question to try to get a better handle on flaring efficiency and how that plays in to various different estimates, but I just want to make that quick comment.
Thank you, Casey. Perhaps I could ask Ricardo to stop sharing the screen because we still have
my apologies. My apologies. I hope I will be able to stop sharing.
No, it's now, and now
okay,
it's
right.
Casey. Perfect. Okay, thank you.
All right, 1 second. I've just had a problem with my, sorry. Oops. Okay, sorry about that. A little hiccup there. So I have a few slides, and I would really like to take one step back from this discussion on baselines and say a few words about the implications for what better baselines and better MRV monitoring and reporting and verification could potentially mean for policymakers. And before getting to those implications, I want to start with just a little bit of context. So earlier this year, the IEA released a roadmap to achieving net zero emissions globally by 2050, based on our net zero scenario, which maps out the actions that could get us there. For methane, we found that emissions from fossil fuel operations would need to fall by around 75% between 2020 and 2030. Reductions in use of fossil fuels, so as in reducing demand for gas, oil, and coal, won't take us fully to where we need to go on its own. And we will need a concerted effort to cut methane to this level in the next decade if the world is to keep 1.5-degree stabilization within reach. So to flesh out this roadmap, we developed a report that we released in October that tries to put some meat on the pathway to how governments can reach these targets, how governments and companies can do this based on a combination of regulation, incentives, diplomacy, and transparency actions. Now, we released this report just before COP26, and as I'm sure you all already know, over 100 countries joined the Global Methane Pledge at COP26. This list here is actually already out of date as new countries have joined since then. And under this pledge, the countries aim to collectively cut anthropogenic sources of methane by 30% by 2030. And of course, we've already started to see questions about how that baseline should be understood for the countries making that pledge. And I'll come back to that in one moment. Since we released that report, there have been, we have updated the analysis to take account of the global methane pledge countries. And one of the things that's quite clear is that the countries that have joined the GMP can do more to address their emissions within their borders, and there are a number of policy options available to help them. To start with, there is a set of well-established policy tools that have already been deployed in multiple jurisdictions, including bans on non-emergency flaring and venting, adopting technology standards to replace high-emitting equipment, and requiring companies to run leak detection and repair programs. From our estimate, these tried and tested policies can cut emissions in half. And critically, these types of policy actions don't necessarily require high quality measured data on emissions, which is similar to the point that Andris mentioned at the beginning of this session that has also been echoed by folks like Jonathan Banks at the Clean Air Task Force. But turning to today's topic, one of the most interesting pieces is that a functional and reliable monitoring, reporting, and verification regime is a prerequisite for certain types of policy tools that can drive deeper cuts in emissions. This includes market-based instruments, performance standards, trade measures at the international level, and these kinds of tools can provide more flexibility to individual countries or companies as they try to comply, and this can lead to more efficient outcomes. They can also open up potential abatement options that are difficult for regulators to mandate directly using things like technology standards and bans on flaring and venting. So the takeaway here is that MRV can facilitate the work of regulators in reaching these additional cuts, but also in verifying compliance and tracking progress against reduction targets. And I wanted to say one additional word about internationally traded oil and gas. In parallel with action on domestic emissions, the global methane pledge countries may also be able to encourage additional reductions further up the value chain, including from countries that aren't members of the GMP. So several of the GMP countries are already large importers of oil and gas, including the EU and Japan, and this provides an opportunity to work with their trading partners to reduce emissions from even outside the borders of these countries. On the policy side, countries with methane commitments can take certain actions to target internationally traded oil and gas using different complementary instruments. This includes things like developing a price premium for oil and gas with a lower emissions intensity, providing financing options to encourage abatement, and adopting market access conditions like emissions intensity requirements. And again, just like in the context of domestic policies, many of these actions, and really all of these actions, rely on robust MRV. So developing these new systems to have better measured data can then enable more efficient and more options on the table for policy action. And finally, in addition, investing in transparency measures like certification programs like OGMP 2.0, and also international efforts such as the International Methane Emissions Observatory that we just heard about a moment ago, can also help to bring additional pressure on companies to take action. So in my view, coming back to the subject of this second half of today's session, trying to think through what the implications would be of if we are successful at improving measurements, reporting, and verification. I think there are at least 3 ways that this better data could lead to more emissions reductions and more concrete reductions. First is that better MRV can identify information gaps and help companies know where the best opportunities are to target reductions. In our work with the methane tracker, and as has been mentioned by a couple others, we found that there are many cases where the value of emitted methane is higher than the cost of the abatement options needed to capture it. So in other words, these options can sometimes be cost effective, but a major challenge is information. Of course, companies can't reduce emissions they don't know about, and equipping companies with better information about where their emission sources lie can encourage them to take voluntary actions, even if they're not required to by regulation. Another potentially interesting area in this regard is the concept of a kind of satellite early warning system that's been proposed in a few contexts. We may not quite be there with the technology yet, but we are approaching the point where satellite technologies can actually spot ongoing leaks and potentially lead to interventions on the ground if that information can get to the right place. The second area is that better MRV can help countries track their progress against their climate goals. So this is really relevant in the context of the global methane pledge, but the baseline here will really be critical. And as Andris and Thomas were discussing in the first part of this session, the credibility of the existing system will be key here. So there's a few different things that need to happen. And the first is it will be necessary to improve monitoring technology and the methodology for calculating and estimating emissions if we're really going to track progress towards this goal. So clearly on the technical side, there are big improvements that can still be made. And there's a lot of different R&D efforts going along, as we've been hearing about in a few different places. But really what we need to do is we need to improve monitoring to bridge the gap between these top-down and bottom-up estimates and really have a more complete understanding of what's going on. The second thing we need to do is not just to improve the technologies, but expand how we're using them. The existing tools that we already have, including on-the-ground surveys, flyover campaigns, can already do a lot to improve our knowledge of emissions, but they're not in wide use yet. And countries and companies really need to invest in deploying the existing technologies alongside investments in improving them. And the third area is, even without new technologies, countries need to invest the time and resources to update their existing UNFCCC inventories. Whether that's based on new technologies and new developments, new measurement or not, some countries haven't updated their inventories in a long time, and keeping these up to date would at least be a first step at developing at improving the situation. And the final point I'd like to make is that MRV can be really important in the area of policy and regulation. This is really building on the points I just made in the past couple slides. In this regard, accurate and reliable data can support more efficient policies and regulation, both domestically and internationally. And this can include the types of policies I described earlier, like emissions pricing and performance standards. But it'll also be vital to ensure enforcement of policies and regulations, including both traditional inspections by government workers, flyover campaigns, and even satellites. There have already been a few cases in the United States where authorities have opened investigations based on satellite detections initially reported in the news media. This is a really interesting development and one we expect to see more often. So in conclusion, over the next few years, we will obviously need to invest more in the tools and methodologies that were discussed as part of this session, and there's really a lot of interesting developments going on. And in our view, there are some clear positive implications in a number of areas that can take us towards, draw the link between better data and clear reductions. And thank you for the opportunity.
Thank you, Casey. I fully agree with this, your conclusions, but I am not this time. I need to struggle to make myself conclusions. We can move now to really finalizing the workshop, and I am very glad that Dagmar Röckmann will make conclusions. She listened very carefully on this very rich presentations. It's not so easy always after 2 hours to make short conclusions, but I know that Dagmar will try its best really to conclude our today's workshop. Dagmar, the floor is yours.
Yeah, thank you, Andris, and thank you for inviting me to do so. And as you say, it's quite a challenging task because we covered so much ground, and arguably I've got 1 minute now to do the conclusions. So I will not summarize every single presentation. I think it's probably good to start always with KC's presentation, because I think he very eloquently made clear why getting MRV right is so important. And again, that's fresh in our minds, so I won't repeat that, but that is ultimately why we're doing this. Improve the data, help to get better policies as a consequence. Maybe, it's about the credibility of the whole system. I think in the presentations, I heard a couple of themes which are really crucial, I feel, for further research. There's clearly a lot of experience using different ways of measuring data. But what came back in almost every single presentation, including on the first one that related to the IPCC report, is that there is still a real need to bring together bottom-up and top-down measurements and to really understand what that means. There's a mismatch, and that's a word that one of the presentators used, between top-down and bottom-up measurements. And one of the presentations, and I think that was Ricardo, made that very clear with the example on flaring. So that is definitely an area for further work. I think for me, the presentation from Manon was quite helpful as well, because that was almost a shopping list of further work that could be done. The encouraging feedback from some of the commentators was that a lot is on the way. And, you know, pressed for time, I would like to sort of say that for me, the overarching question almost is that it's great that so much research is happening, that new work is on the way, but there is a real need to bring this together and to have someone or something to have a holistic view of what is out there. And I think for me, that is where the presentation from Stephen Hamburg came in, because we now have an opportunity through IMEO to bring all the different sources together, where that relates to OGMP 2.0 data, where it relates to all the different measurements to techniques, but also the science studies and inventory data. And perhaps that's the right way of concluding that all the work that is happening out there should come together. And by doing that, it also means that we've got a further opportunity to see if there's still outstanding gaps where we need to improve MRV for this really important issue. So I hope that was short enough, Andris, and I excuses to everyone who I've ignored a little bit in my summary, but I hope that sort of brings together what we've all talked about.
Yeah, thank you, Dagmar. From me, I would just, I know that we are an audience that agree mostly with each other, but I think when we became speakers before the workshop, we talked a lot about COVID-19. And I think one of the lessons that everybody should learn from COVID-19, please provide facts and based on science, because when you are late, you can't anymore explain for the people who are confused with the information and unfortunately take wrong conclusions. So I believe at least in climate fight area, we'll still have this opportunity, but I believe that we should really also support the inventories, that they are correct, that people base their decisions on the facts, and that will provide for a more smoother transition of energy system and general economic system towards to sustainability. I would like to conclude thanking everybody who participated in today's workshop. I really appreciate all the speakers. They really did a fantastic job. And I hope that today's recording will be seen many, many times, because there have been a lot of valuable information and also very valuable conclusions for the policymakers as well. Thank you very much, and well, have a nice evening, everybody.